Hello everyone, welcome to this lecture series in integral calculus. This is second lecture and we are going to talk about applications of definite integral. In the last lecture, with the help of definite integrals, we calculated area under the curve and area between two curves. Okay. Uh, in this lecture, we are going to extend the applications to find volumes or length of arcs or surface areas. Okay. So first, about the volumes, we can find the volumes of solids using the areas of the cross sections. Okay. The cross sectional area is usually a plane region, and we are going to discuss three methods to find this cross sectional area. The three methods are by slicing the parallel planes, or the disk method, or the washer method. Okay. And once we have the cross sectional area, then we can integrate from the point A to B to find the volume. Okay. So first, let us talk about the method of slicing to find the cross-sectional area and how we can calculate volume using that. Okay. So to this end, suppose that we want to find the volume of a solid S. Okay. So say this whole thing is your volume S. Okay, solid S, and this solid is defined for point x is equal to a to x is equal to b. Okay, so this interval AB along the x-axis, we will partition this interval. Okay, so we partition AB into sub intervals of width delta xk. Okay, and then we slice the solid by planes perpendicular to x-axis at the partition points. Okay, so like if we partition it, and we already discussed in the last lecture that we can partition the interval by taking points x naught, x1, so on xn. Okay, where x naught is a and xn is b, and such that x naught is strictly less than x1, is less than x2, and so on, less than xn. Okay, and so delta xk are the width of each partition, and so delta xk will be like xk minus xk minus 1. Okay, and at each of the points x naught, x1, x2, so on. Okay, so we cut this solid with the perpendicular plane. So let this be the in general any point of the partition, and we cut it like a plane. Okay, so here we this will generate a cross sectional area when this plane will cut this solid. Okay, we can approximate the slab between the uh, xk minus 1 and plane xk by a cylindrical solid with base area axk and height delta xk. Okay, so if on the kth partition, okay, which is from xk minus 1 to xk, if we cut this solid with at the point xk minus 1 and xk, so it will generate this slab whose base will be this base area will be the area of cross section, and a height will be simply xk minus 1 to xk, that means delta x. Okay, delta xk. And so we can calculate this product as this cross sectional area axk times delta xk, and if we calculate all such cross sectional areas and add them up, so that will be the entire volume, and that entire volume is written as a Riemann sum. Okay, so the volume of this uh, slab, which is between xk minus 1 to xk, is the cross-sectional area axk into delta xk. Okay, so this cross-sectional area here multiplied with this width delta xk, so that will be the volume of this slab, and if we add all such volumes, then we can write the Riemann sum, which is summation k from 1 to n of this volume. Okay, and so the volume of the entire solid will be simply the Riemann sum written as this. Okay, and then we know if we take uh, the partition, each partition, if we represent the norm of the partition, and if we take the norm of partition going to 0, that means n going large, then we have seen this in the previous lecture, that we can represent that as an integral. Okay, so as norm of the partition goes to 0, this summation can be represented as an integral, and integral of ax dx, where integral goes right from a to b. Okay, so the volume of the solid can be calculated as integral from a to b of ax dx, where ax is the area of the cross section uh, at any point x between a and b. Okay, so now we can I can just rewrite this definition, and so the volume of a solid of integrable cross-sectional area ax. Okay, so if you can find the cross-sectional area, which will be a function of x, of course, so that has to be a integrable function, and from x equal to a to x is equal to b, if we integrate this area, then we'll get exactly the volume of the solid. So volume of the solid will be integral a to b ax dx, where this integrand ax must be a integrable function. Okay, so how to calculate the volume? So you need to just uh, do these four simple steps, that you first sketch the solid and see what the typical cross section is. Okay, and find the formula for the cross section, which is ax. Okay, and then find the limits. Okay, the limits of x from what point to what point. If we move on x, we will complete the whole volume. Okay, so if I move from a to b, this plane, then it will cover the whole volume, right? So this cross sectional area, which is a function of x, when we move, it will take the shape of that object there. And so if we integrate with this formula, integrate the ax over limit a to b, we will get the whole volume of the solid. Okay, say for example, uh, say a pyramid of 3 meter high has a square base that is 3 meter on a side. Okay, the cross section of the pyramid perpendicular to the altitude x meter down from the vertex is a square x meter on a side. Find the volume of pyramid. Okay, so there is a pyramid which is 3 meter height. Okay, so this is the base of the pyramid. Okay, and it's a 3 meter height, and the base is a 3 meter on a side. Okay, so that's why it is 3 meter on this side. Okay, so base is a square of each side 3 meter, and the height of the pyramid is 3. Okay, so instead of drawing it like vertical, we have just drawn it along the x-axis. Okay, and it is said that at any point x, if we cut by a plane, then the cross-sectional area is x meter on a side. So if at any point x we cut this or slice this, then it will slice like a square whose uh, cross-sectional area is square x meter. Okay, so it's x by x. Okay, so you can clearly see that at any point x, if we cut, then cross-sectional area ax is x into x, because it's cutting it like a square. So x square is ax, and if I integrate this x square from x0 to x3, then I will get the whole volume of this pyramid. Okay, so if first we sketch, we draw the pyramid with its altitude along the x-axis and its vertex at origin, and include a typical cross section, a formula for the cross sectional area. Okay, so if at any point x, cross section is x meter on a side, so area is definitely x square. And if I integrate this from a to b, where a is 0 and b is 3, then uh, we'll get the volume of this pyramid. Okay, so integral of x square is simple, x cubed by 3, and then we know by definition that I will substitute the upper limit and minus the lower limit. Okay, so that will give us that total volume of this pyramid. Say take one more example here. Say a curved wedge is cut from a circular cylinder of radius 3 by two planes. Okay, so these two planes are like one plane is perpendicular to the axis of the cylinder. The second plane crosses the first plane at a 45 degree at the center of the cylinder. Okay, so find the volume of the wedge. So you can clearly see that this is the geometry, that you have a cylinder of radius 3 units with center at origin. Okay, and so you have this cylindrical part, and two planes cut it. Okay, one which is perpendicular to axis of cylinder, so that's why this base uh, will be there because of that. Okay, and the other at 45 degrees, so other is this one which cuts it at a 45-degree angle, and it crosses at the center of the cylinder, so it passes through origin. So this plane and the ground plane, they cut the cylinder into this wedge shape. Okay, and we have to find the volume of this wedge. So if we slice this wedge with at any point x between 0 and 3, where 3 is the radius, right? So at any point x, if we slice this plane, then this slice will cut into a cross-sectional area of a rectangle uh, with at any point x, the angle is 45 degree with this wedge, so perpendicular we can this the height can be calculated as perpendicular by base, which is tangent of 45, so perpendicular immediately is same as base. Okay, so perpendicular is also x, and the length of the rectangle uh, for any point on the circle with the point here x, so corresponding point on this circular cylinder will be x minus root of 9 minus x square. So we have the edge point here, so similarly the other edge point will be plus of this, so this length will be nothing but 2 times root of 9 minus x square. Okay, so we have the uh, length and breadth of the rectangle, so we immediately have the cross-sectional area, which is x times 2 times root of 9 minus x square. And once we have the cross-sectional area, then we can integrate it from the limits of x, which is 0 to 3. That will give us the volume. Okay, so the area of cross-section is height into width, okay, which is 2x root of 9 minus x square. Okay, because length width is this 2 times 9 minus x square, and height is x. Okay, and the rectangles will run from x0 to x3 to cover this whole volume. Okay, so we can find the volume by integrating the cross-sectional area from 0 to 3. Okay, so ax is already calculated, and so we can integrate this and substitute upper limit minus lower limit to find that the volume of the wedge is 18. Okay, so this is the first method, the method of slicing to calculate the volume. Okay, using the cross-sectional area. Okay, the second method to find volume using cross-sectional areas is the uh, method of disk method, when the solid is uh, revolved about a plane region, about the axis of the plane region. Okay, so if the solid generated by rotating or revolving a plane region about an axis in its plane is called the solid of revolution. For example, if you look at this geometry, if this is the solid, this is a plane region. Okay, on the xy plane, if there is a region which is bounded by some curves, say for example y is equal to root x in this example, y 0 and x is equal to 4, these three curves uh, generate a plane region, this blue, okay. And if this plane region is rotated, okay, here in this figure it is shown that it is rotated about the x-axis, okay. So basically it is rotated about an axis in its plane, okay. So any axis or any line in its plane, so this y is equal to 0, or x-axis is the line in its plane. So if it is rotated about that line, then it will generate a volume, okay. So this plane, this curve, this x-axis and this line, this has a this a plane region. When it is rotated about uh, the x-axis, it will create or generate this volume, okay. So we want to find the volume of this solid region generated by this plane, okay. So if I take any point x uh, on this line, then the corresponding y value will be known, okay, from the function curve, okay. So if it is a fx curve, then y is equal to fx will be the value corresponding here for any point x, okay. And when this line will be rotated about this x-axis, so you can see that this will generate a disk here, okay. And this disk, the cross-sectional area, we know that for this disk the area will be pi r square. Pi times radius square is the area of the disk. And so if you know the radius, then you can easily write the cross-sectional area, and then the volume can be calculated by integrating from the point A to point B the cross-sectional area, whatever cross-sectional area is, okay. So volume by disk for rotation about x-axis, okay. So if we are rotating about the x-axis, the volume will be integral A to B of the cross-sectional area dx, okay. And in this case the cross-sectional area is a disk, and for a disk the area is pi times radius square, okay. So the volume can be calculated as integral A to B pi r square dx, where r is a function of x because it is calculated for general point x between A and B, okay. Similarly, if the object is rotated about the uh, y-axis, okay, so the similar formula we can write, the radial will be a function of y, and we will be integrating with respect to y from some point C to some point D, the y values, okay. So the volume of the disk for rotating about the y-axis can be written similarly as integral of cross-sectional area times dy, where y varies from C point to D point, okay. So, and cross-sectional area is again pi r square because it is generating a disk whose area is pi r square, okay. Say for example, if you have this plane region bounded by these four curves here, and it is rotated about the y-axis, okay, where because that axis is part of the region, okay. So at any point y between 1 and 4, okay, uh, we will have a corresponding x as a function of y, and it, if we rotate this, it will create a disk here whose cross-sectional area, okay, like this, cross-sectional area is pi ry square, okay. And then we can integrate from lower point to upper point, which is point C to D, which is looked as 1 to 4 here, and that will give us the volume of the solid of revolution, okay. So let us take one example to see this. Let find the volume of solid generated by revolving the region bounded by y is equal to root x, and the lines y is equal to 1, x is equal to 4 about the line y is equal to 1, okay. So see, there is a curve y is equal to root x. So if you draw this curve, this will be the curve y is equal to root x, okay. There is a line y is equal to 1, so that's this line y is equal to 1, and there is a line x is equal to 4, so x is equal to 4. So clearly you can see that the region is bounded by these three curves. So you can see that this is the region which is bounded by y is equal to root x, y is equal to 1, and x is equal to 4, okay. And it is said that if this plane region is rotated about y is equal to 1 line, and y is equal to 1 line is uh, is part of this plane. So if it is rotated, if this region is rotated about this line, it will generate a volume whose cross-sectional area at any general point will be a disk. Okay, so uh, if you rotate this about this line, you will see that it will generate a volume of this form, where at any general point the cross-sectional area will be disk. Okay, so cross-sectional area will be pi r square, okay, the area of this disk. And we just need to find what is the radius here, this length. Okay, and square of this times pi will be the cross-sectional area, and then we can integrate it from x value a to x value b. Okay, and you can see that x value at a is x is equal to 1 from this volume area, or volume will start, and x is equal to 4 will be the point where the volume will end. Okay, so we can simply integrate from 1 to 4 pi r square, and you can see what is a radial here. Okay, the radial is this length, which is root x minus 1. Okay, so this distance. So the volume is integral 1 to 4 pi r square dx, where r is a function of x, this radial. And so that radial is here root x minus 1. Okay, so we can simply square this and integrate this to find the result. Okay, so squaring this term, now integral of x is x square by 2, integral of x half is x 3 by 2 by 3 by 2, integral of 1 is x. So we can then substitute the limits. Okay, the upper limit x value as 4 here, minus the x value 1, and then we can solve it to see the volume is 7 pi by 3. Okay. Okay, so I take one more example here. Say, find the volume of the solid generated by revolving the region between the parabola and line x is equal to 3, about the line x is equal to 3. Okay, so region is bounded between these two curves. Okay, so there is a parabola and a line. So you can see that line x is equal to 3 is here, and uh, parabola is x is equal to y square plus 1, which is this parabola. Okay, and so the region bounded between these two is this region. Okay, and this region is rotated about the line x is equal to 3, about this line. So this line is part of the region. So when this will be rotated here, it will generate a disk, and this whole region when rotated will generate a volume. Okay, so if you know this radial, then you can find the cross-sectional area of the disk, and then you can integrate uh, with y values. Okay, so clearly you can see that the radial will be the y value here minus the y value here, and y value here is sorry, the x value here minus x value here. So x value here is 3, and x value here is y square plus 1. So 3 minus y square plus 1, which is 2 minus y square, is this radial. And we can integrate this pi times square of this dy with y varying from c to d, where c is the lower point where we enter this volume, and d is the upper point when we leave this volume. Okay, so it will generate this volume with cross-sectional area from here. Okay, and we'll enter at this point and we'll leave at this point. Okay, so by substituting x as 3, uh, we can calculate the y values, which are the points of intersection here. Okay, and so we can integrate from y minus root 2 to y plus root 2. Okay, so the volume will be minus root 2 to root 2, the cross-sectional area pi ry square dy. Okay, and ry is there, 2 minus y square. So we can square it, and then we can integrate. Integral of 4 is 4y, y square is y cube by 3, y4 is y4 by 5, and then substitute the upper limit minus substitute the y value as lower limit, and then solve that, and you can see that the volume is 64 root 2 by 15 times pi. Okay, so this was uh, the second method to find volume by using disk. Okay. uh, Disk, you can see, is generated when we rotated the region about one of the axes of that region. Okay, but if we rotate it about some line which is not part of the plane region, then it will not generate a disk, but it will generate a washer. Okay, so that's what our third method is. Okay, the washer method. Okay, so if the region we revolve to generate a solid does not border on or cross the axis of the revolution, the solid has a hole in it. Okay, say for example, if you have a region this bounded by curves, okay, and if we rotate it about say x-axis as shown here, okay, but x-axis is not a curve which lie on the border or on this plane region. Okay, so when it is rotated about this axis, okay, this whole region, then it will generate this volume which has a hole inside. Okay, because of this distance, this, when it will be rotated, it will create a hole here. Okay, so in this case we have to calculate two radii, okay, from the axis about line about which this object or this region is rotated. There will be two radii, one from this axis up to the nearest curve and other from this axis up to the farthest curve. Okay, so the volume or the area of cross section will be area of cross section of this washer. Okay, which will depend on two radii. One is the radii, the inner radii, and the other is the outer radii. Okay, and so the area of cross section will be the area inside the outer radii, and the minus the area which is of the area of the hole. Okay, so if we consider this as a disk like, so you can calculate the total area minus the area of the hole. Okay, so pi times r, capital R square, will be the total area of disk, minus pi times small r square, which is the area of the hole. If we subtract, we will get the area of the washer. Okay, so the cross-sectional perpendicular to the axis of revolving or washer instead of disk. Okay, so we all talked about it. So volume by washers for rotation about x-axis. Okay, it will be the integral from a to b ax dx, where area of cross-section is now uh, the area of disk minus the pi times small r square, the area of the hole. Okay, so if we remove the area of the hole, then we will get the area of the washer. Okay, so the formula is slightly modified because of the hole present inside the volume. Okay, and similarly, if you rotate the object about the y-axis, then similar formula can be written in terms of y, integrating with y from c to d. Okay, so the volume of washers for rotation about the y-axis will be integral of the cross-section area from c to d. In that case, it will be pi capital R square minus small r square. Okay, so pi times capital R square is like area of disk, minus pi times small r square is the area of the hole, which is subtracted from this to find the cross-sectional area of the washer, which is integrated from C to D to find the total volume. Okay, so again, say for example, say the region bounded by curve and this line is revolved about the x-axis to generate a solid. Find the volume of solid. Okay, so what you have to draw is first draw this parabola and line and see what are the regions bounded by this on xy plane, and then if we rotate this region about the x-axis. Okay, so first thing is whether this x-axis lies on the border or on this plane. If it is, then cross-sectional area will be simply a disk. If it is not, then the cross-sectional area will be a washer. Okay, so you can see that this is the y is equal to x square plus 1 curve, and this is y is equal to minus x plus 3 curve. So area or the region bounded is this region, and this region is rotated about the x-axis. X-axis is here. Okay, so if this is rotated about the x-axis, it will, because x-axis is not lying on the boundary or on the plane region, so it will generate a washer. Okay, so we have to calculate two radii here. Okay, so for any first we have to find the points of intersection of two curves. Okay, so we can like substitute y here and then solve it to find x values. So you can find that x is equal to minus 2y5 will satisfy this, and x1 y2 satisfies. So you have the end points. So x varies from minus 2 to 1. So if I take any x value between minus 2 and 1, then you can calculate what is the smaller radius or the radial of the hole generated and the outer radius. Okay, so that will be from um, x-axis to up to here, this distance. Okay, so this distance we know is from this curve, which is y is equal to minus x plus 3. So upper radial is minus x plus 3, and this smaller radial will be the y value from here. Okay, and y is x square plus 1, so this radial is x square plus 1. And then we can calculate the area of the washer will be the area from this, which is pi times this square that will generate the disk, minus the area of the hole. So pi of times this square is subtracted from pi times this square. Okay, so outer radius this, inner radius this. Okay, and the limit of integration will be x, which is minus 2 to 1, x is varying. And the formula for volume is a to b pi r square minus pi r square dx. Okay, so the disk area minus the whole area, okay, will be the washer area. Okay, and capital R and small r we know, so we can simply substitute. We can solve this, and then we can integrate from for x from minus 2 to 1 to find the volume. Okay, so a simple integration, and then substitute upper limit minus substitute x value as lower limit and solve. Okay, so 117 by 5 pi is the volume of the solid generated by revolving this plane region. Okay, so now so far we did three methods. Okay, uh, where we calculated the cross-sectional area, and we integrated the cross-sectional area to generate the or calculate the volume. Okay, now there is another method which is called the shell method, where instead of uh, calculating uh, the cross-sectional area by slicing or by rotating uh, and generating a disk or a washer, instead we calculate uh, by slicing with a circular cylinder. Okay, so let us try to understand this. Say suppose the region bounded by graph of a non-negative continuous function y is equal to fx, and the x-axis over a finite closed interval AB lies to the right of a vertical line x is equal to L about this curve is rotated. Okay, so let us see what we mean. Say there is a curve y is equal to fx, which is a non-negative continuous function. Okay, so this curve lies above the x-axis. Okay, from the point A to point B. Okay, and so the region bounded between the curve, the x-axis, and the line x is equal to a and x is equal to b will be this region. Okay, and if this region is rotated about a line x is equal to L, where x is equal to L is a line which lies uh, to the left of the point A, or at most it can be the point, it can be the line this x is equal to A. Okay, so there is a condition that A must be greater than equal to L, so that the vertical line may touch the region at this line x is equal to A, but not pass through it. Okay, so this line will not lie on the right of A. okay, it will be either x is equal to a line or it will be on the left of this line. Okay, we generate a solid S by rotating this region about the vertical line L. Okay, so if this region is rotated about this line L, it will generate a volume. Okay, now to find out that volume using shell method, by using the cylindrical shells, okay, we partition this interval a to b, and we know how to do the partition by taking point x naught at a, then x1, x2, x3, so on xn at b. Okay, so let p be a partition of the interval ab and ck be the midpoint of the kth subinterval xk minus 1 xk. So this will be your kth subinterval xk minus 1 to xk, and ck, let it be the midpoint of this interval. So at ck you can find the corresponding function value, which will be fxk, we can write yk as fxk. Okay, and with this width, if we draw a rectangle of height f of ck, okay, then when this whole region will be rotated, this rectangular region will rotate to generate a cylindrical shell. Okay, so a typical approximation of rectangle has height fck and width delta xk, and when this will be rotated, if rectangle is rotated about the vertical line x is equal to L, then a shell is swept out. Okay, so you can see that this rectangular region, when it is rotated about this line, this rectangular region will generate this uh, cylindrical shell. Okay, and the volume of this cylindrical shell will be this area times this circumference, okay, which is 2 pi r. Okay, the circumference times the area of this rectangular region. Okay, so that's shell height into thickness. Okay, so shell height into thickness. Okay, so you can see that thickness is delta xk minus xk minus 1. Okay, so this thickness is delta xk. So the volume of this cylindrical shell is 2 pi times the shell radius. Okay, if it is rotated, then this will be the radius from x is equal to L to this. Okay, that will be the radius, and shell height, which is here this height, okay, fck, and thickness is delta xk. So uh, if we add up all such cylindrical radius, okay, so there will be another partition here, another height that will also generate cylinder, there will be another here which will also generate a cylinder. So if we add all such cylindrical shells, it will generate us the whole volume of the solid. Okay, so the total volume will be the Riemann sum of the cylindrical shells. Okay, so it will be k is equal to 1 to n delta vk, and then if we take the norm of the partition tending to 0, okay, so or n tending to infinity, that means then we can write it as a integral from a to b of uh, delta vk, which is integral of from a to b of 2 pi times shell radius times shell height times dx, because delta xk will turn into dx. Okay, so now we are in a position to write the definition clearly. What you need is that the function is non-negative continuous. Okay, and there is a condition that L is less than equal to A and A is less than B. Okay, so L is less than A is less than B, and then we can calculate the volume by this formula. Okay, so shell formula for revolving about the vertical line, okay, will be based on conditions that the y is equal to fx has to be non-negative, and the this plane area between x-axis and fx from A to B is rotated about a vertical line, that vertical line lies to the left of A or at most at A, okay, then the volume can be calculated by this formula, integral from A to B of 2 pi times shell radius times shell height dx. Okay, so we are not specifying what is shell radius and shell height. So if you take any point x between A and B, I can calculate the height there, so that will be shell height, and I can calculate the radial from x to L, that will be shell radius, and then I can integrate to find the total volume. Okay, similarly, if instead of vertical line, if we rotate about a horizontal line, so we can write the similar formula, which will be c to d 2 pi times shell radius times shell height integrated with y dy. Okay, so let us see one example on this. Say the region bounded by the curve y is equal to root x, the x-axis, and the line x is equal to 4 is revolved about the y-axis to generate a solid. Find the volume of solid. Okay, so say you are given that y is equal to root x, is a curve, and the x-axis, which is this, and x is equal to 4. Okay, so these three uh, lines and curve together uh, bounds a region, which is this region, and if this region is revolved about the y-axis, okay, so revolved about this axis here, okay, so this whole region will revolve like this. Okay, so it will generate a volume. So if I take any x point between 0 and 4, okay, so immediately I will have this shell height, okay, and I will have this shell radius, okay, because radius will be x from the line about which it is rotated, and you can see that this line when rotated will generate this cylindrical shell. Okay, so once I have this shell height and this shell radius, then I can apply the formula for volume to calculate my result. Okay, so the volume is A to B 2 pi shell radius shell height dx. Okay, you can clearly see that the this radius is x, distance from 0, so that's x. Shell height is at any x point, this height will be the value of y from this formula, so shell height is nothing but root x. So shell radius is x, shell height is root x, so we just need to integrate from 0 to 4 2 pi x root x dx. So it, if we combine this, it is x power 3 by 2. We can integrate that. Okay, so it will be x power 5 by 2 by 5 by 2. Okay, 0 to 4, upper limit x value 4 minus lower limit x value 0. Okay, we can solve that to find that the volume is 1 by 128 by 5 pi. Okay, uh, next thing that we want to calculate is length of a curve. Okay, so if you are given a curve y is equal to fx, where the curve varying from x value a to x value b, so say for example you have a curve this, okay, y is equal to fx, which goes right from x is equal to a to x is equal to b, and we want to find uh, the length of this curve. Okay, so suppose that the curve we wish to whose length we wish to find is the graph of this function from x is equal to x to b. Okay, so for this we have to assume that the curve or the function that represents this curve has a continuous derivative at every point of uh, the domain AB. Okay, so we assume fx has continuous derivative at every point of the interval a to b. Okay, this will make sure that the curve is smooth. Okay, that means there are no breaks or no corners or no cusps in this curve. Okay, so again, if we partition this curve, okay, by points x0, x1, x2, so on xn, such that x0 is a and xn is b. Okay, so let p be a partition of av with this. Okay, that's how we do the partition. So and uh, so if yk is equal to fxk. Okay, so at any point xk, the corresponding point on the curve will be xk comma yk, which we can calculate from the function value. So yk is fxk, will be the point pk, which is xk comma yk. Okay, and this point lies on the curve. Okay, so if we draw all such points, okay, at x0, x1, x2, so on, and join the successive points by straight lines. Okay, so pk minus 1 pk by straight line, and similarly so x0 x1 by straight line, x1 x2 by straight line, and so on. Okay, all the points, successive points by straight lines, then together all these straight lines will form a polygon path whose length will approximate the length of curve when these points will become large, okay, in number. Okay, so when these points will be uh, uh, close to each other, then the curve and straight lines can be approximated. We have already done this, the concept of linearization. So if the partition norm goes to 0, or equivalently you can say when n becomes large, the number of points are uh, going to infinity, that means these points are very close to each other, then these straight lines and the curve path can be approximated, and so the total length of polygon path and the length of curve will be approximately same. Okay, so we can approximate in that way. Okay, so if xk, oh, so here I think delta xk, okay, xk minus xk minus 1, okay, which we know is delta xk, and yk minus 1, which is delta yk. Okay, so delta signs are missed here. Okay, so delta xk is this, and delta yk is this. Okay, then the kth segment will have the length this. Okay, because if this is your delta x distance, and the corresponding points we said is pk minus 1 and pk, and so this will be your line joining these 2 points. So if this length we know is delta xk, and the corresponding length here is delta yk, so by you can see right angle triangle, this length of lk will be delta x square plus delta y square root. Okay, so we can write this. Okay, so if we uh, add all such lines lk's, okay, then that will be Riemann sum from k1 to n. Okay, so the total length of the curve will be the Riemann sum, which is total length is k1 to n of lk's, or this. Okay, and so if we take non p tending to 0 or n tends to infinity, then we can replace it as an integral from a to b of uh, this root of, if I take delta x outside this, then 1 plus dy by dx squared into dx, or if I take delta y outside, then 1 plus dx by dy squared root dy. Okay, so we can write in terms of x as well as in terms of y. Okay, so in general, if I have to write it in short, that the length of the curve y is equal to fx when x varies from a to b, if the function has continuous derivative. Okay, so f dash x is continuous on ab. Okay, that means the curve is smooth, then the arc length or length of curve y is equal to fx from point a to b is the value of this integral a to b integral 1 plus f dash x square dx, or we can say a to b in root of 1 plus dy by dx square dx. Okay, and similarly, if we have to write in terms of y, then we can easily rewrite this, the length of curve, as integral c to d root of 1 plus dx by dy square of dy. Okay, so either you can use this formula or this formula to calculate the length of the curve. Okay, say for example, find the length of the graph of function fx is equal to x cubed by 12 plus 1 by x, x varies from 1 to 4. So if you just plot this curve, then this curve with x varying from 1 to 4, so we just want to know the length of curve from point A to point B. Okay, so this length of curve we can calculate. We need a derivative of this, so first derivative will be x square by 4 minus 1 by x square, and then we can use the formula that uh, the length of the curve will be root of 1 plus f dash square. So if you calculate f1 plus f dash square from here, okay, so 1 plus this f dash value squared, we can square it, uh, add a 1, and then we can rewrite it as a whole square. Okay, so the length of curve by formula is integral a to b, where a to b x value is 1 to 4, root of 1 plus f dash square dx, and 1 plus f dash square is this whole square, so whole square and root will be simply this value x square by 4 plus 1 by x square. So if we can now simply integrate, okay, and then substitute the upper limit for x minus the lower limit of x, and we can calculate that the length of the curve from a to b is 6 units. Okay, finally, we take one last topic is to find the area of the surface of revolution when it is rotated about the x-axis and or rotated about the y-axis. So if you have a function which is non-negative, continuously differentiable on the interval AB, the area of the surface generated by revolving the curve about x-axis is given by this formula. Okay, so if you just remember that if you if you rotate about x-axis, we can do this similarly. If you take the partition of AB, and then in the kth partition xk minus 1 to xk, we will have a small portion of the curve. If that will be rotated about the x-axis, we will have a surface area generated, and that surface area will be the 2 pi r times the arc length. So it's like 2 pi function times arc length, which when integrated from the point A to point B will generate the whole surface area. Okay, so by partition we can calculate the area of the first term, and then we can integrate to find the whole surface area. Okay, similarly, if you have x as a function of y, which is continuous from point C to D, then with a similar definition we can calculate the area when it is rotated about y-axis by integrating with respect to y from C to D. Okay, let's see this through an example. Say, find the area of the surface generated by revolving the curve y is equal to 2 root x, where x varies from 1 to 2 about x-axis. Okay, so there is a curve from x is equal to 1 to 2 given by this formula, and if it is rotated about x-axis, it will generate a surface whose area we need to calculate. Okay, so like this is the curve, y is equal to 2 root x, but we only need the portion of the curve from x1 to 2. So from this point to this point is the curve. When it is rotated about the x-axis, okay, it will generate this surface whose area we need to calculate, this area. Okay, this area. So the formula says that we just need to find the integral from a to b 2 pi function times root of 1 plus f dash x squared dx. Okay, so that's like this will be 2 pi r, okay, for any point x. Okay, this any point x here between 1 and 2, there will be, this will be your radial, which is fx. So 2 pi fx will be this radial plus arc into arc length will be the area. Okay, integrated. So function is known, fx is 2 root x. We can calculate derivative, substitute and integrate from 1 to 2. Okay, so a is 1, b is 2, y is 2 root x. So first derivative f dash x, which is dy by dx, is 1 by root x. So we can just plug everything here and we can integrate. Okay, so 2 root x is y and 1 by root x here. Okay, so we'll have 4 pi this will be 1 by x, so we'll have x plus 1 by x root, so root x will cancel out and we'll simply have root of x plus 1. So we can integrate this. X plus 1 half will be 3 by 2 by 3 by 2. Okay, and so x value 2 upper limit minus x value 1 lower limit. Okay, so that will be the surface area generated by revolving this curve about the x-axis. Okay, so I guess this was about the applications of definite integrals. So we now know how to calculate volumes, surface areas, uh, length of the curves. Okay, in the next lecture we'll talk about double integrals. Okay, so till then, take care, have a very good day.